So I welcome you to another episode of the CU Web Seminar Series with the title A Comparative Study on the Application of Carbon Fiber Reinforced Thermoplastic and Thermoset Components, presented to you by Sebastian Bühler, CTO of Bionic Composite Technology AG, Biontec. And questions can be asked at the end of the presentation, or they can be sent via chat, and I'm going to read them afterwards, and Sebastian is going to answer the questions to you. And I wish you an exciting presentation and hand over to Sebastian Bühler. Sebastian, stage is yours.
Thank you very much, Theo, for this nice introduction. Also from my side, good morning to everybody. Today, as Theo mentioned, I want to talk about a comparative study on the application of carbon fiber reinforced thermoplastic and thermoset components. This project or investigation was done together with OST. You see on the right side, you see our logo on the top, and down you see below you see the OST Rapperswil together with John Barandun and his team. First of all, before I go deep in detail, I would like to give you a short introduction of Biontec. From haute couture to high tech, what does that mean? We have a very strong heritage in stitching. The Forster Group, since 125 years, we are located in St. Gallen, and we do embroidery textiles for the clothing industry. We transferred this knowledge of embroidery technology to the technical stitching, the so-called tailored fiber placement, the biomimetic fiber placement. And we believe due to the behavior of the anisotropic behavior of the fiber, that we can align the fiber in the perfect direction. And the tailored fiber placement process is the suitable way to do that. So result at the end of the day is an outstanding performance. We have a high repeatability of the parts, and we are able to stitch a lot of needles parallel. We are able to reach for series up to more than 100,000 parts a year. On the right side, at the top, you see the embroidery line of for the clothing industry, and below the tailored fiber placement. Here you see the clamping force, but I will show you later on. Where are we located? We are worldwide active. At the top here, the Forster Group. In there we are the Biontec Composite Technology AG, or short Biontec. We have our headquarters here in St. Gallen. As you can see here on this photo, this is the whole Forster Group, and on the right side you see the Biontec. Also, we have a production site in Nantong in Suzhou. There we are always also develop, but mainly produce composite parts. And below we have a production site in Romania. In Romania we focus on preforming and on the tailored fiber placement process. To give you an impression, how does that look in our production? Because we would like to, or we produce composite parts. You see a small insight in our facility here. On the left side, we have the embroidery machines. Here you see we can, it's a very huge machine. We can stitch with more than 30 needles parallel, the same shape. So we are very, very efficient. And when we have filled the whole fabric, Then we do a preforming. This is done in the other hall, not shown in this picture here. And on the other side, if you go to the right side, we see our own designed RTM machines. These designed especially for our process. Yeah, so we have everything in-house. After the RTM process, normally it's necessary to machine the parts, and below you see one CNC machine. Now the department is growing and growing, and in the meantime we have more than 2 CNC machines, and yeah, what is not shown here is the deburring and the finishing department, but I think you all are familiar with that. Yeah, we believe development and product management should come from Switzerland, so we do. We have 8 engineers in-house, which are mainly all experts in composites, material experts, process experts. We develop the concept of a part for our customer. Then, of course, we design and do the construction on common CAD programs, and afterwards, of course, we do the dimensioning, because this is a very, very important point for us, because we are looking for the load path and the main forces, that we can align the fibers in the perfect way, because our philosophy is not only to look for an isotropic laminate. We want to have unidirectional fibers in every layer, and we would like to place the material in where it is really needed. And after the dimensioning and the tool design, we also do in-house. We do the validation of the prototypes, and of course we manufacture the prototypes in-house, and then normally the parts go to our customers, and they do their in-house testing, and then we start to install the serious production. When we talk about tailored fiber placement, then I have in mind always very complex carbon fiber reinforced parts, and the tailored fiber placement process makes serial production possible. Here you can see only 4 examples of composite parts. We have, on the one side, we have the brake lever from the sport and leisure industry. We have a measurement device, as you can see on the left. We have industry parts, and many, many more. All parts have in common that they are complex, that they have complex load paths, and where the tailored fiber placement process is necessary to gain a very lightweight part. And we believe that our Biontec technology, or tailored fiber placement, combined with the RTM process, is suitable up from 100 parts a year up to more than 50,000, 100,000 parts a year. That's really not a big challenge or issue for us. Yeah, what are the industry needs today? Of course, always, first of all, we would like to make the parts lighter from our customers, but of course, there's always stiffness is very important, and strength. In many cases, we have the benign failure is also very important. The fatigue strength is also very important, and yeah, the design and aesthetic aspects with carbon fiber parts comes on its own because we do it bionic in a bionic way, and so we have mainly nice surfaces. But also sustainability is a very, very important point, and of course the recycling. One word to the recycling point. we make or we have some projects in-house where we stitch recycled carbon fibers, and we achieved very, very nice parts. So if there are any interest, please let me know after the presentation. I think it's a very nice story here we can tell also to our customers. Yeah, I talked a little bit about the technology. Of course, tailored fiber placement is the focus in our technology setup because we believe our unique selling point is that we can do the tailored fiber placement, and because with that we can produce our own textile. And to give you just an idea, we have in-house two routes, the blue one and the orange one. I will start with the blue route. It's the classic thermoset route. We use any kinds of dry fibers from the roving or the yarn, and then we stitch the layer on the top of each other, and we can, in every layer, we can achieve the perfect orientation of the fibers. Then with less preforms and the net-shaped geometry, we can go in an accurate preforming. This is depending on the part. For the break lever here, for example, it's quite easy because it's only one layup. And with this dry preform and 3D preform, we then go in the RTM mold and inject the resin. If we go for the thermoplastic route, then our starting material here is not a dry fiber. It is a commingled yarn. And again, it's the same way, load pass aligned the fibers. We can stitch again several layers on the top of each other. The preforming step is quite the same compared to the thermoset way. And then with that preforming, we go in hot pressing. I will show you later on with more details. Under pressure and high temperature, we can consolidate the final part. What is not shown on the picture, but you have seen on the foil where we have the impression of our production site. After that, we do a CNC machine. Yeah, tailored fiber placement. I think a lot of you are familiar with that. Here we see the clamping mechanism of the brake lever. It's a very, very nice part for the tailored fiber placement because here you can see we can continuously stitch the fibers around the hole. We can be net shaped. We are very precise, and once the process is installed, then we are very automatically, we have a very automatic process, and it's very, very robust. Of course, as you can see here, okay, it's a small part, but we have nearly no cutting waste. It's just this yarn which is going out of the shape and going in the next shape. This is only the cut of, mainly we talk about 2 to 3% of the carbon waste. So I think the tailored fiber placement in itself is a very sustainable way to gain a composite part. Yeah, the tailored fiber placement makes us possible for accurate preforming. Here you can see more in detail so perfect orientation of the fibers around the hole and around here the small gap here. And yeah, the only thing we have to handle with the tailored fiber placement, we need a substrate or a back material on which we stitch our carbon fibers. In some cases, it's necessary that we have to get rid of the back material. And in some cases, it's necessary that, for example, a glass fabric has to stay in the part. Then, of course, we have a bit more of cutting waste. But yeah, the substrate is very, very thin. We are about 40 grams per square meter. So this is a very, very lightweight substrate. Yeah, you can wash it out, you can burn it out. And in former times from the textile industries, they also used acetone, but this is, yeah, because of recycling and sustainability, not the perfect way for us. Coming to our very important point is the consolidation. You see always blue is the thermoset route, and the orange is the hot press or the thermoplastic route. As you can see, for the RTM, we use our own machines. Of course, we have a chemical reaction. We mainly use the light RTM or high pressure RTM. That depends a little bit on the thickness of the part. And for prototypes, of course, we can use a Vari system. Temperature usually around 80 to 150 degrees for our main parts. Some parts are a little bit higher, but mainly we are around this temperature area. And of course, every RTM process, but I think you're familiar with that, the injection unit is necessary. The preferred material for the mold is depending on the part and the surface quality of the part, and of course of the mold output and how long and how many parts we have to produce per year. If we start in the engineering or the development phase, often we use a polymer mold. For the prototypes, then we or start of production, we often use an aluminum tool, and later on, if we gain for higher volumes, then often we transfer this to a steel mold. But also aluminum mold is capable for more than 2,000 parts a year. So aluminum has also its advantages. On the other side, for the hot pressing process, of course, we have to be heating up above the TG of the thermoplast. Normally, we use, because we are doing complex composite parts, we have to use engineering or technical polymer. So often we have to handle with higher TGs. So the temperature usually is above 180 degrees. Mainly in the case I will show you later on, we are about 200 degrees. Of course, because we have higher consolidation pressure, we need a hydraulic press. So we are not able to design our RTM or our presses on our own. So as you can see on the right picture below, we use a standard hot press, and of course the required tooling mainly is steel. This is the introduction of the technology, and now I would like to come to the case study, what we investigated together with Ost and Rapperswil. And yeah, Mainly in our cases for our customers, we use the carbon fiber, but after that, a main question is asked or also skipped in sometimes whether we can use a thermoset or a thermoplastic polymer, and we ask ourselves, which matrix shall I use? And for that, we had in mind that we would like to do a one-to-one comparison, and therefore we did this comparative study, and we would like to illustrate the advantages and the disadvantages of each metric system, and of course the required processing, because at the end of the day we would like to produce the parts. And therefore we decided that we want to use a tension element, as you can see on the right side. I think here you can see the dimension in the camera. So it's a very, very thin part. We have two sections. We have the leg section and we have the loop. The part is, has only one load case. We have unfortunately minimal design space, but of course it's optimal for tailored fiber placement because we can align the fiber along the shape of the part, and we have the continuous flow of the fibers. We choose for the thermoset setup, we used a high tenacity fiber with 400 ticks, a standard epoxy resin, and standard stitching yarn. And for the thermoplastic route, we choose also a high tenacity fiber, but here called from the supplier, it's a carbon fiber with a PA12, the polyamide 12 hybrid yarn with 588 tacks. Unfortunately, it was only available to have stapled fiber, but we will later on we will see how influences the behavior of the part. What we learned that of course we need a stitching yarn, and here we learned that if the stitching yarn is quite the same like the matrix system, then we have only a duo material system, and this is from the processing side, it's more easy to handle than if you have another stitching yarn with another thermoplastic or a cotton or something like that. Coming to the tailored fiber placement, when we do the design of the program and the filling, then of course we have to look how many fibers do we get into the part, into the volume. As I mentioned before, you see we have divided the part in two sections. On the one side, it's a leg, and above you see it's a loop. And we see that especially for the thermoplastic route, because we bring the thermoplastic and the matrix directly in the mold, we do not inject the resin afterwards. We have to do an overfilling. And for the leg section, we had to do overfilling of 164%, and in the loop, it was only 133%. And the amount of hybrid yarn with the commingled yarn has to be adjusted very precisely for every cross section in a part. For the thermoset route, it's a bit easier in the design phase because the stitch textiles have nearly the thickness of the final part, and again, we see that in the moment we have a little bit more freedom and choice in the combining of multi-materials. we have more fibers available. With the thermoplastic side, there's often a combination. Yeah, we have to buy from the supplier the composite or the carbon fiber compared to the matrix. Coming to the preforming, again, the thermoset route, of course, we are a little bit lighter than the thermoplastic, because here we only have the fibers, and on the thermoplastic side, we have the overfilling, and of course, we have still the matrix in the preform. For the thermoset, we have a very, very thin preform, and because we have no overfilling of the cavity, of course, the thermoplastic is a bit thicker, and this leads that the textile is a bit stiffer, so the drapability, especially for this thin part, is a bit poorer than than for the only for the textile, for the thermoset route. Below you see the picture. After here you see the preforms. They are stitched. Still the white the white yarn is a stitching yarn, and you see the substrate in this case was washed away. And after a drying process, then you have a warping of the preforms, and before we put it in the mold, we stretch the preforms a little bit, and then we can put it directly in the mold, but we will see this on the next page. So consolidation process, the thermoset process, the temperature is about 100 degrees. We have a cycle time of roughly about 1 hour. We use, of course, a demolding agent, and of course, the curing of the resin system takes some time. Below the picture, you see we have a 5-cavity mold. We have the injection of the resin here, and then the resin goes through the part, and here's the outlet. And yeah, here you see a more detailed photo, the loop. Here you see we have a resin-rich area, but this is okay in that case, because we have to align the fibers here around the loop. For the thermoplastic route, of course, we have to install a higher temperature because polyamide 12 is melting by roughly about 215 to 220 degrees. Still, and that was very surprising, we had still also a cycle time of 1 hour, because you can't or it's in the moment it's not possible that we can do the preforming in the hot mold. So we have to cool down the mold. In this case we have a steel mold, also for the thermoset route, and therefore we have always to cool down the process, then do the preforming, and then heat up again and do the consolidation. And yeah, as some of you perhaps are familiar with that, if you consolidate a commingled yarn, you can't just close the mold. You have a sequential pressing, because you have to get rid of the voids and the air in the preform, and this has to go step by step. Coming to the part quality, of course, the thermoset part quality, this is our classic way. We are very familiar with that, and the repeatability of the tolerance is very, very high. We have a very high quality of the surface, as you can see on the picture below. the only material we lost is the outflow of the resin and the fiber orientation, because in that case we use a very low pressure for the injection. We have a very precise orientation of the fibers. For the thermoplastic route, we have after the demolding, we have for warping of the part a little bit, because this is due to the thickness of the part, because it's very thin. At the beginning, we had some surface irregularities, but later on we gained a very nice surface. As you can see here, it's quite a nice surface. And yeah, we had to handle a very high amount of material outflow. And later on, a big question is the fiber orientation due to the pressing. What is happening there? Can we still keep the fibers in the perfect direction? We want to have them later on in the part as we have designed it. And below you see a picture. When we started with the process, we saw that we see here in the picture we have the resin outflow here on the top, and we have not gained enough overfilling and not enough pressure, and we see some voids here. So the consolidation is not so bad. Not so good, and at the end of the project, and for all the thermoplastic parts we do today, we have a cross section like this on the right side here. Here we have no voids anymore. It's a perfect consolidated cross section. Yeah, last but not least, I would like to give you an impression of the part characterization and the behavior of the thermoset continuous fibers and the commingled fibers, stapled yarn. Therefore, we used our in-house testing machine. We have 10 samples tested each for the thermoplastic route and the thermoset route. The tensile test has not a supported loop above here. And the tensile testing machine was the Shimatsu AG-X plus 20 kilonewton, and the test up is here in St. Gallen. If we look a little bit deeper in the mechanical performance for the thermoset, at the end of the day, we have a weight of every part after we have deburred and finished the part. We have 1.52 grams per part. And the fiber volume fraction, okay, it's calculated because we have no measurement device available in-house. We have 41%, and we gained a maximum force of 3,700 Newton. And the stiffness was around 37 gigapascal, and the failure mode was a shear failure or compression shear failure in the loop, as you can see on the picture below. If you would support this, then you could minimize that, but this failure mode without a supported loop, this is expected failure mode from literature. On the right side, you see the 10 samples. As you can see, on the x-axis the displacement in millimeter, and on the y-axis the force. And as you can see, the statistic is very narrow, and we have only a slight variation of the mechanical performance. The mechanical performance of the thermoplastic parts, the weight is a bit higher because also in the gap here and the edges here, we have more material, so we are a little bit we have a little bit more weight, but yeah, of course, the fiber volume fraction is a bit higher than compared to the thermoset. But the mechanical performance is mainly driven by the stapled yarn, because we have a tension element and we have not the continuous fibers. Then you see that we have much lower maximum force. As you can see, it's about 2000 Newton, and the stiffness is around 61 gigapascal, so also a little bit lower than with the thermoset and the continuous fibers. And we saw another behavior of the failure and the material. We have the failure in the leg section, not in the loop, and yeah, and with all the 10 samples, we have the same failure mode. Yeah, this is on the one side driven by the staple fibers, and on the other side a little bit on the warping of the part after the demolding. Coming to the conclusion of my presentation, I think we have with thermoset and also with thermoplastic, we have two very, very interesting matrices. And we learned that the combination of commingled yarn with the stitching yarns needs to be carefully considered. So I talked about the overfilling. I talked about the overflow out of the mold. The handling is easier than with the thermoset polymers, because we only have the press process. We do not have to go and use the injection unit. We have no degassing of the material, so we have a closed process, and it's a very clean process. Of course, the pressing process we investigated and saw the best chances to gain a very nice part is the biothermal process, and the pressing time is increased due to the high temperature for the thermoplastic matrix. Demolding at elevated temperature leads to a deformation of thin parts, as I mentioned before. As you can see here, the part is very thin. If we would have a bigger part, then I think the deformation and the warping would be less. Also, we see that the complexity to the hot pressing tool is limited because, yeah, with the thermoset process, we can have very, very complex parts. The resin flows nearly everywhere because the viscosity is very low. And with the pressing process, so you have a multi-inlay tool pressing from several sides. That makes the pressing tool a little bit more complicated, or limited the complexity of a thermoset part. For the RTM of the thermoset parts, tailored fiber placement, of course, is a little bit faster, because we only stitch the fibers and not the matrix, and the volume fraction is around 50%. And of course, the continuous fibers shows a better mechanical performance compared to the stable fibers. For the future, where do we want to go? I think two technologies in parallel with both, using the potential of tailored fiber placement. We can stitch both materials. We can orientate the fibers with the tailored fiber placement process in a very perfect way. And yeah, I think we should do more investigation of the orientation of the fibers after the press process. If are there all the fibers in that location we have designed it, and do we have any ondulation, or did we lose any fibers with the outflow of the resin and the matrix. This is, I think, needs a bit more investigation. And yeah, of course, the further development of the thermoplastic route is necessary. Now we have installed our own press here, and we have our first customer process here. And we learned from this project that we reduced the outflow of the material, and of course the part is a bit bigger than the tension element here, and we saw that yeah, the warping of the part is not existing anymore. Yeah, at the end of the day, expanding the choice and availability of hybrid yarns. I think this is very important to all the guys out there who supplies the material. And yeah, later on, mainly we do mechanical parts, but if we want to paint them or something like that, then the surface finish has to be considered. And of course, for the RTM process, as I mentioned at the beginning of my presentation, the recycling and bio-based epoxy and the recycling of the carbon fibers is on the horizon. And I think there are a lot of ways to design sustainable and nice composite part. At the very end, I would like to thank the partners, especially the Institute of Werkstoffkunde, Institute for Materials Technology and Plastic Processing in Rapperswil, especially for Claudio Corbiseri for his work, and for Professor John Barandun, also for the InnoSwiss agency. For this project, we get an innovation check. You can find the application title under Last optimierte Composite auf der Basis von Hybridgarnen, and this was sponsored by 50,000 Swiss francs. Thank you very much for your attention, and yeah, I'm very happy and looking for all the questions. And yeah, Theo, I think it's your turn.